Hello and welcome to discussion number 7, topic 7, in a series on Introduction to Artificial Intelligence topics that I've been going through. It's going pretty quickly. So trying to keep them in a certain amount of a logical order. Sometimes there's some deviations that you'd kind of like to do different, but you go with it. So moving on, we're to something that anytime you see the word simple or fundamental or elementary in a slide, it always makes you cringe, right? Because those are sometimes some of the most challenging topics to get through. In this case, we're kind of setting up the foundations for decision making. So we start off with a relatively simplistic approach and then make it better. So we've talked to some extent about the things that you need to do. And as always, good resources. The text that I would recommend is they're from the instructors at Berkeley, as are these slides came from. So you would be well suited to take a look at this AI book. It is kind of the definitive book. So we've been talking about this for a bit from the perspective of an agent, right? And it's all about kind of combining together your beliefs, so what you think to be the state of the world, and some sort of desire under uncertainty. So you've got something you would like to get, but you don't necessarily know for sure that, first of all, that the reality is what you think it is. Secondly, you may not necessarily know how to get there well. So that's where we use this concept of utility. We've talked a little bit about it before. So a question is, whenever you're calculating an expected maximum utility, is it something that you should average or not, or should you be using min max? And I think it would come down to, are you expecting that it's always going to be a zero sum game, right? So are you always going to be in competitive arrangements with your environment? And that may not be the case. So instead, maybe average it instead. And what that'll do is that it maximizes the expected utility given its knowledge, right? That's the basic idea. So a rational agent should. That's a very specific definition of what something is. And then you have some obviously questions that will fall off of that. Where do utilities come from? How do we know such utilities even exist? And can you quantify them? How do you know the average even makes sense? Does the average of a utility that you're attempting to maximize the expected utility of, does it make sense whenever you think of it in terms of an average? Then what if our behavior preferences can't be described by utilities? And you likely are going to want to introduce some sort of surrogate of whatever it is you're trying to really accomplish. So the basis of utility theorem, and what utilities to use. So when you're picking, you have a choice sometimes between the worst case min-max reasoning and the terminal function scale. That doesn't matter. So the long story short, you want to do better states. You want to have states that have higher evaluations so that you get the ordering correct, is what you're basically wanting to do. And we call this insensitivity to monotonic transformations. So trying to make sure you get the order of operations correct, and that the average case or expecting max reasoning, we need magnitudes to be meaningful. And sometimes just getting on the right scale is what matters. So utilities are functions from outcomes, so states of the world, that we're trying to get to a real number that describes a preference. So given A or B, which is better, right? And that's really what we're trying to get to here, is coming up with a way of quantifying that. So that's what the function is. Something takes in an observation about a condition of the world, maybe some outcome that is a change in that condition, and is it better than the other thing? So you need some way of being able to quantify. So it could be simple, positive or negative sort of things, where if you lose pieces, it's a negative thing, as an example. It may be summarized the agent's goal. So maybe it's getting pieces to one piece of the board is something that you're trying to do. So getting all of your pieces to go across. maybe one of your utilities might be the number of pieces that are beyond halfway or something. So anyway, it's got to be something that's rational and it's a preference. So something you're trying to obtain that is predictable, rational, and right thinking is how you would think of it. You may hardwire these utilities and then let the behaviors that minimize or maximize those utilities figure it out themselves, almost like an evolutionary sort of approach. And why would you not let an agent pick the utilities? They may not know what's important to you. And but we may not want to tell them what to do because we may want them to figure it out. They may be able to come up with some approaches that are better than what we have in mind. So we oftentimes, in this case, of you're getting an ice cream cone and you have the more is better, right? More scoops is obviously going to be better. There's obviously going to, and this is a time honored decision tree criteria of how many scoops of ice cream do I get. So if you get the one, you have perhaps a higher probability of it staying. If you go to get a double, you might maybe lose your first scoop, which would be bad, or maybe not. So you've got some uncertainty. And obviously a way of ranking each of these outcomes, the least desirable being no ice cream. Assuming you don't dislike chocolate, the one scoop of strawberry would be better. Then obviously the more is always going to be better from a general perspective. So when we talk about utility functions, it's about expressing of a preference of a state. And so you may think of it in as far as various ways to annotate that sort of preference. And the main thing is trying to get it such that you can have a preference. Obviously, in a lottery, your preference would be to win. And so you have a preference among various prizes, and there's obviously some uncertainty associated with these prizes. So the probability of A and the probability of B is 1 minus the probability of A. And so and odds are going to be that the probability of A is much smaller. So P is going to be pretty small compared to 1 minus P. But there is a way of noting this stuff, a notation. So your preference is going to be of obviously A over B. If you don't care, you may put the tilde. Whenever we're coming up with this rationality, you're going to come up with some sort of way of doing a plan. Obviously, you have your axioms of transitivity, which do apply with preferences. So you want some constraint on the preferences before we can call them rational, such as some way of stating what these things, how they behave. That's going to be something that you're going to want to do, is make sure as you're coming up with your way of representing your preferences, making sure that that representation is rational, and not all preferences may be rational. So we may need some other way of representing what it is that we're trying to accomplish, because we do want the preferences, any kind of these observations and or behaviors that are taken based upon observations. We always want that to be a rational thing. And you can expect that the rational, and it's a reasonable thing to say that a rational preferences is going to imply behavior describable as maximization of expected utility. So you're basically saying that a set of rational preferences is going to result in, hopefully, a description of the behavior that will also be a maximization of expected utility. And it's we're rationally certifying a little robot there. Let's do this, go a little quicker. So probably, I think we've kind of drained the concept of utility. So the basic idea of when we're doing these decisions is coming up with some way of representing a desired state. Money is a good way of describing. Um, it may not have itself a utility function, but odds are going to be that you're going to want to maximize it, right? We can talk about the utility of having money or being in debt. So you can talk about the greater the outcome of a monetary transaction, the better, as a general rule. And there's also risk associated with certain activities. So some behaviors are going to potentially have higher utility, but also may entail higher risk. So you may want to think about the concept of insurance. Of given, do you want to minimize your uncertainty and essentially try to turn things into a win-win scenario whereby using insurance, you're minimizing your risk and also kind of maximizing your overall outcome. And oftentimes, this rationale is actually what organizations do. They hedge their bets in some fashion. And that's essentially what this insurance premium would be. If you're an international firm dealing with monetary exchange rates, you might find ways to try to protect against uncertainty in the various markets. So lots of different ways that stuff may be done. So we're talking about making decisions, and we're finally kind of back to the topic of decisions, because you really, in order to make decisions, first of all, have to talk about that utility and the concepts of behavior related to utility. When we talk about decisions, there's various ways that we make decisions, but generally there's some sort of relationship between them, and we call that oftentimes a network. We use networks and graphs a lot in artificial intelligence as a way of modeling relatively complex behaviors and observations. So when we talk about it, then it's about kind of a mixture of forecasts and so on. So if you've got a forecast for weather, or maybe a forecast for a sunny day, you have a choice between taking your beach ball or taking your umbrella. So maybe you only can take one. And it's going to be where there's a decision factor that's going to be based upon, the weather is being forecasted by, so some sort of probabilistic belief in a certain outcome of the weather. And related to a certain weather state is the need or desire for an umbrella. So your basic idea of a decision network is to try to essentially maximize the expected utility of the given, based upon the given evidence. So you have a set of things that you're observing. You have probabilities, so chance nodes, and we were adding that in as this circle. So there's a certain probability associated with things that are in the circle, so forecast and weather. You have a utility node, and then also actions. So we're coming up with a way of essentially modeling decision making in networks, right? And using essentially a very simplistic edge-based graph to do it with different types of nodes. Now we've extended it a little bit. So we talk about essentially actions, right? It's going to be about instantiate all the evidence at action nodes, the action at each way possible. So you switch them back and forth. Calculate the posterior for all of the parents of the utility node given the evidence, calculate the expected utility for each action, and then choose the maximizing action. So you would come up with some sort of probability matrix, then some actions associated with, so either leave or take. It depends upon the various, essentially the combination of actions and based upon what actually outcome turns to be, and then basically figure out what is the various states of taking or leaving the umbrella, and calculating that in this case you probably don't need the umbrella based upon the probabilities. That's not to say so that we choose leave based upon just it's got the higher probability. You can then think of these decisions a slightly different view as a tree. So turning it into a tree and then essentially working our way down as we deal with more and more complex things, always attempting to maximize the expected utility. So some relatively complex stuff, but the key things is that you want to take away is that you can organize your decision-making process and your actions that can be taken, the belief about a condition, so something that has a probabilistic characteristic, such as the weather, and then make a decision based upon those things. So we've talked a bit about making decisions. Another thing that we do when we're making decisions is think about the value of information, understanding that the value of information may change over time. So the way is the basic thing that we're coming up with is you've got an idea and you're going to compute a value of acquiring evidence. And this can be done directly from Decision Network. So an example of buying oil drilling rights. So you likely would want to make a choice ahead of time of how many essentially which one of the blocks has your oil is what we're basically coming up with. So you've got two blocks. One of them has oil. One of them has a certain worth. So A and B, exactly one has oil, right, which has a worth of K. So to restate it one more time, you can drill in one location. You don't know anything about the prior probability. So it's a 50-50 chance and mutually exclusive. So do you drill or do you not? And then you have a series of potential outcomes. You're going to hit oil or you're not. So what is the value of information of O, of figuring out if the value is there or not? And we do have K as well, right? So so the value of knowing which of A or B has oil, value is expected gain in MEU from new information. So you've got some new information. It adjusts the current value associated with something. So a survey may say oil is in A or oil is in B, and each of those again has a probabilistic value. If we know that or the values, right, either way, whatever they might be, then we can start coming up with a way of calculating the gain, so which would be K over 2. So the fair price of the information would be half of the value of the oil is the logic. What is the value of perfect information? It's a way that you can come up with it, because sometimes you have to just settle for good enough. So it's about gathering additional information and knowing what the outcome of the value is by having gathered some additional information. And so we can come up with ways of quantifying the value of information. And it's all going to be a question of assuming that you have some evidence. The value, if we act now, is the formula is shown. And then the value, if we act then, so this is calculating in the time, so on. So while that it is a random value, we don't know what E prime is going to be. But we can if we basically rewrite the formulas. And then the value of information is how much EU goes up by revealing E prime, then acting over, then first, then acting over acting now. So you may want to wait or not is what it comes down to, and you're trying to figure out the impact that time has on value. and depending upon the interplays, it may be more complicated, and it may be that it will be decreasing in value, but it may not. It's going to depend upon the relationship of what other things are known as well. So the soup of the day is either clam chowder or split pea, but you wouldn't order either one. What's the value of knowing which it is? Probably not that much because you don't really care. There are two kinds of plastic forks at a picnic. One is kind of slightly sturdier than the other. What's the value of knowing which is which? Probably depends on what it is you're eating. And so if it's something hard like a steak, then it's probably going to be more important to know which is which. You're playing the lottery and the prize will be $0 or $100. You can play any number between 1 and 100, so your chance is 1% of winning. But what is the value of knowing the winning number? So you can come up with a way of quantifying what these values are. So what is the value of imperfect information? There's no such thing. So information corresponds to observable knowledge about a decision network. The data may be noisy. That just means we didn't observe the original value. Rather, you're observing some other value. So it may be not as good as you would like, and maybe you're observing a side effect. But so you can start answering some different question. You may also have a challenge with preference. You may not know what the preference is. So you've got a set of observed variables. The agent may not know what things have what value, so to speak. So it becomes probabilistic, or some challenges. You do probabilistic calculations over this to figure it out. So with this, we've talked a bit about how we make decisions that are relatively simple. And you can see this, again, things that say they're simple, not always all that simple, right? But it is a foundation for building on with more complex decision making. Keeping in mind that it's all about kind of an understanding of evidence. What are the things that we know? What is the value of information? How does learning something new change the value of information? And what can you do with that whenever you're trying to come up with an agent that's going to intelligently behave in a world? So a rationally operating agent. With that, if you have any questions, let me know. Hope you found this interesting. Any feedback, feel free to shoot it to me as a note or whatever else. I look forward to it, and thank you for watching.